Today, I'm going to talk about mapping in unconventional play areas. So my name is Connor Burt. I'm a technical sales geoscientist with Petrosys USA. I've got a background in development geology and some more lab-related digital rock analysis, and then now I'm working my way to being your go-to Petrosys guru. And we're going to go ahead and talk about a few things. We sent out a little teaser video during the ERTech virtual conference a few weeks back or a month back, kind of related to this. And so we'll look at that analysis. It was a short video, and then we'll dive into a little more detailed analysis. So the agenda today will be to go over just a quick Petrosys overview. I'll try to touch on some of the main points and just leave the slides up long enough that if later you want to watch this back and pause the video, you can get that information. Then we'll go into the unconventional analysis example. We'll look at the one from the ERTech video that was sort of a limited well data example driven by our seismic attribute analysis. But then we'll integrate data from other sources. So we've got some actual well data, some cuttings and core data, and some surface data that we can include. And we'll test some of our assumptions, and we'll just see kind of what made this play work. Then the next thing will be getting into surface modeling and basically showing how we went through that process of testing those assumptions. We can grid our structures, do some porosity and saturation gridding, and then finally get some area-based volumetrics. And then at the end, we'll kind of go over what are some ways we could take this further, and how can we change the analysis, and then into questions. And with that, I will go ahead and cut my camera off just to give you less distractions on the screen. So the quick overview for Petrosys is our product suite. Petrosys PRO is our flagship desktop mapping and surface modeling platform. That's what we'll be working in today. We do have some OEM level software packages that integrate directly to Petrel and Esri. Then we also have an E&P data management platform called dbMap, and a portfolio management platform called PLDB for managing all of your prospects and leads. We won't talk too much about these today, but just know that they are available to you. And in the last 12 months, we've also added some seismic processing in the form of Globe Claritas, and then some project archiving technology through Interica. So the Petrosys PRO value proposition, we can step through all of these piece by piece, but I just wanted to get them onto the recording. You can check them later. But what I'll say is that really the value proposition is high quality maps, versatility of data, and being able to actually generate accurate surface models, accurate volumes, and being able to share those things easily and with the proper quality. We talked a little bit there, versatility in maps was something, or versatility of data, but also versatility of maps. Kind of our bread and butter historically has been reservoir maps, being able to overlay all the different layers you need, including the structures, the thickness, in addition to fault layers and any surface layer data. And what we'll do is actually today we'll explore using some of those same techniques to evaluate unconventional reservoirs. So the log signature maps is another type of map that we produce. This is something that we don't have the log curves to look at today, but it's a way of actually looking at rock properties across your entire field area, across your entire map, and actually posting them directly where their location is, so you can see how things are changing across your field area. And then another example would be bubble mapping. So production mapping, being able to load that information and plot it this way is a really nice way to visually just seeing what are the differences across an area, are different platforms performing better than others? Are different well pads performing better than others, or is it different intervals? And last but not least, an important part of the equation is the integration of spatial and subsurface data. So the ability to say, take the satellite imagery we see here and put our well pads with our laterals and our directional wells, and being able to actually see how those interact with our own, let's say, our company acreage, for example, or just with other surface things like roads and buildings, which can be really important, especially in certain areas where there's limitations on where you can drill. And with that, I'll go into the spatial modeling for unconventional development. So you might begin with some regional fairway mapping. So this is sort of a repeat from the video that went out before, but we'll go through it. Over the large area, you want to make sure that you have a thick, regionally extensive, mature source rock. Then you want to make sure you have some kind of reservoir interval, something that you can actually produce from. And in this case, it's actually just an adjacent reservoir just above the source rock from this example. And when you overlay those with different pressure parameters or different maturity windows, you can start to get some good fairways identified. And the example that we'll look at today is actually in northern Alberta, which is where this other example is from as well, but it's a slightly different interval. So here's our field location. You can see it just kind of the northern edge of Alberta. This is actually Edmonton down here in the bottom right corner. This is going to be kind of the shape of our field. This is our 3D seismic extent with a structure map laid within it. And we're going to try to get to some drilling targets. So if we approach this from a standpoint of what data do we have, we've got some structure maps from the regional seismic. We have some total organic carbon estimates from actual seismic attributes. We have thermal maturity. We have oil and gas windows based on that thermal maturity. And then we have some 3D seismic attributes. So we've got amplitude extraction and organics attribute, a seismic curvature for looking at things like fractures or if there's any erosional features. And then a potential liquids attribute based off the acoustic impedance. I don't know the secret sauce that went into it, but basically it's a look at potential liquids. But where does this data come from? So interpreted horizons and well pick for our top structure, so that's well data and seismic data. And the TOC, as I said, was from some seismic attributes, but also from core and cuttings later on in the field development. The thermal maturity comes from vitrinite reflectance and the burial history of the basin, so we kind of know what the temperature gradient is and how far it's been buried. And then the oil and gas windows. So these are generic sort of maturity levels, and as we may see later, that some of these need to be expanded or contracted just based on the type of organic carbon that's present. And then we also have everything coming in from the 3D seismic, all of the attributes coming from the same place. If we take this without looking at any well data, let's say we don't have either we have sparse well information or no well information, we can just start to get an idea for what's around. So in this case, we've got the dry gas window, the wet gas window, and the oil window. And we want to high grade maybe based on just our liquids rich areas. So we can take those polygons and just extract them. But then we want to compare it to, say, a TOC trend, making sure that we have the appropriate parameters we need to generate plenty of oil. And then we can start to evaluate a little bit more closely. We have some primary, now a secondary. So a little bit higher TOC, still pretty good though in the lower area. So not off the grid, but still considered secondary. And then we can even grade it further based on potential things like, in this case, either a large fracture or a fault that might be problematic when it comes to completions. So in the end, we can make a recommendation and start to come up with a well plan. However, we actually have well data in this area, so this would be the sort of the test. So how are our assumptions when we didn't look at the well data? And then we'll see that to the west there, where we didn't put any really spend any time evaluating in the last piece, that's where actually the primary completions are. And what this tells us is we look at the structure map, there's actually a structural component that was really not incorporated in the previous evaluation. And it becomes really important because this is maybe not a classic, but it definitely falls within the classification of basin center gas accumulation. And it actually is a very wet gas and condensate rich. So even though it was in the dry gas or thought to be the dry gas area, there's a lot of quite a few liquids even in that part. And then now we also have an additional source of data, which is well picks and target zone attributes to provide us some data for volume calculations. And with that, we'll go into a little demo to show how we actually go about this. And I'll just give a quick teaser. So first, we're going to generate some grids, structure, thickness, and porosity. Then we're going to go into volumetrics so we can look at the gross rock volume, some of the hydrocarbon pore feet, and then get some volumetrics per area. And then we'll look at while we're doing that, we'll look through the surface modeling workflows, and that's going to show us the task list and how to loop over different factors. Okay, so I will get out of the presentation mode from PowerPoint. And you should be able to see my Petrosys window here. So I've got the launcher and behind it, the map window. So we're in the mapping window now, so I'll go ahead and minimize that. So we're in the Western Canadian Basin, Northern Alberta, and we can see here our lease areas. This is where our company, our company has acreage that we're evaluating this for. And here's all the wells that have been drilled in the area. So the first thing we want to do is start to understand what these wells are and if they actually are within our interval that we're interested in, our target interval. So I can open up my wells, and from the display parameters, I can actually make a data selection. So in this case, I've got my whole, every well in the area displayed. I can select based on where my actual zone picks are. So I've got well tops for a certain interval, the Wilrich. So when I apply that, now I know where all the wells are that I have picked for this for this interval. And this will become important because then I can actually grid using just these wells and ignore the wells that don't have the picks that I want. So that will bring us into surface modeling. So we'll look at this task. So within surface modeling, we have a task list here, and just for visibility, I will increase the size of my text. And we're going to want to actually begin gridding some structures. So in this case, I'm going to look at the top target structure here, and I'll expand this so that you can read everything. And the top target structure grid, we'll look at the inputs for that. So in this case, we actually have seismic data and well data. So this will be applying the well data that we didn't use previously. Within this input data, we can see that there's a WDF and an SDF. So what are those? The WDF is our well data file, so it's our Petrosys formatted well data file, and the seismic data file, which is our Petrosys seismic data file. And what's important to remember is we can use this data selection, and we can use the actual zones that we want to include. So in that case, what we'll do is we'll just look at actually how we got to this point, or actually how we're going to get to the grid, and we'll look at some of the clipping. We're going to clip it to the production area because we don't have data really outside of that area. And we're going to add some contours so we can make sure that we have a contour file for this. So when I run this, it's going to tell me that I'm overwriting a file I've already generated. So it's going to extract well values from every single well, and then it's going to give me a preview file. And if I want, I can come in and delete some of these files that might, or some of these points that look like maybe they're out of place, or I can just say, you know what, I don't know enough, I'll go ahead and grid. So when that's done, I can start to look at my structure map here. And I've got structures here. And here's the top of my target, applied with all the wells laid on top of it. So we can see that actually the lower structural area here is pretty prevalent when it comes to the development. And so that kind of, that lines up with our basin-centered gas accumulation idea. The next thing we want to do is now look at, okay, well, what's the thickness so that we can start to get towards some volumetrics. And so I won't go through every task in the list here, but what we can see is, in addition to my top target, I also can generate some of my base structures. So we have some phantom gridding. This is an example where we don't have a lot of data, so we use some assumptions based on the surrounding well-constrained data sets. So we can create a phantom grid and then apply whatever shifts we need to apply. So coming up with this thickness, we have fairly simple grid arithmetic. It's just a grid 1 minus grid 2 gives us the isocore thickness. And when we do that, we can then start to apply different porosity, water saturation, gas saturation grids to it. So back in mapping, we have a thickness grid. So turn off my top structure, turn on the thickness grid, and we can see that there's actually, need to turn on some contours here. And right now it just looks like it's kind of a smooth data set, so we need to know what are our values. So if I label these contours and I choose a size that might be appropriate, in this case maybe 8 millimeters, and I look at the number of decimal places, probably a 0 here, click OK, we can see that now we go, okay, so now it looks like our thickest area is here, our thinnest area is here. We might actually want to change our color map there. So let's change that to something a little bit more representative. I tend to lean towards hot colors being my thickest or my most attractive areas, or most, the sort of the hot spots, if you will. So let's go with something a little different, but let's go with red to blue, but we'll flip it around and we apply. So now we can see that maybe the thickest area is different. Okay. So really there isn't a thickness trend to go with the well. So the thickness doesn't completely correlate. So now we have to see, well, is there another feature? Is it the porosity? Is it the gas saturation? And when we want to look at these things, we want to make sure we have well data for these. So we have some porosity. We know we have some gas saturation. So I'll look at the well. This is our WDF well data, so well data file editor. And we won't go through too much filtering here, but what I can do is open up a well data file. And I can see now that I've got a whole list of wells here. And if I want, I can actually begin to filter it on zone data. So maybe I look at the zones here and I can see that I have a bunch of different zones. Okay, well, what if I want to do it on zone attributes? Now I can see what zone attributes I can filter on. And in this case, I have porosity, I have some V shale, some thermal maturity and TOC, and then some saturations, and that's really what I'm after today. And within surface modeling, I just open a new one. Let's keep going on the original one. I can now see that I have a porosity grid and some water saturation, gas saturation grids that I'm building. So this data actually, it's going to look very similar to the inputs for the other ones. the only thing that is different is our inputs are going to have zone attribute information. And so here's where we can actually say, okay, I've got my laterals WDF, I've got my selection file, and then the data type that I want to use. So instead of just picking a top or picking a depth, we can go with zones, any kind of attribute or velocity. In this case, porosity. So we've got all my attributes that we saw in the WDF populated here. So when I apply this, we end up with the porosity grid, and I can actually run through the next few steps. I want to show basically that I can what we did. So we've got a porosity grid. We can run through, and using those same attributes, we can create a water saturation grid. So let's look at those in the map window. So let's look at this porosity grid here. So within the porosity grid, we can see that there's actually a really interesting high porosity trend here. And we'll notice that the porosities range from about about 18% to 25, 26%. So it's actually quite good porosity. However, it's a really low permeability sand. So this is like nanodarcy, single nanodarcy scale, tens of nanodarcy scale permeabilities. And then I can look at my gas saturation as well, just to see kind of what it looks like. And those actually line up really nicely. And so that's actually a good sign for us. And we'll go back into surface modeling. And we'll see that within we'll see that we want to actually now apply this to get some thicknesses. So what we want to get is our pore column height, or VH. And so we'll take this data, and using grid arithmetic, we'll just add them together. So let's start from our porosity. So we've generated our porosity grid. Now we want to generate all these other grids, including our pore feet. Then we want to get a SOPH, or in this case, an SG VH. So it's going to be, we want to get our thickness times our porosity times our saturation, so that we get a hydrocarbon column height. And I can select all of these to run. And actually, let's do this instead. I can run from this point and continue on, but I will actually uncheck these bottom ones for now. So let's go ahead and start with the water saturation grid. And we'll just let it run through. And so this is the beauty of the task list, is I can run them individually and test all my different scenarios as I want. But I can also just set it up to run automatically. So now we're generating all these grids, but I won't actually run the volumetrics just yet. So this last map of the gas saturation pore height, so this is going to be the hydrocarbon column, is this map here. And you'll see that this is kind of a different color map. So this is experimenting a little bit with what we call visually perceptive color gradients. They're just something that gives your eye is more used to looking at than a Roy G. Biv type of color map that we've kind of gotten accustomed to. But our natural visual tendencies lean towards these softer gradients. What we can see here, that this area actually where we have most of the wells is where we have the greatest hydrocarbon column. What's interesting is that down here to the south, we actually have a little bit lower, not really explained away by this. So this is something we might look at later after we go through this analysis. But really what I want to know is, in my different lease areas, I've got these 5 different lease areas. What are the volumetrics for each area? So I could get a comparison of okay, well, this is what it looks like on the map. Visually, it seems as though these wells are going to be our most productive, but what's the actual result? And so what I can look at is the volumetrics portion of our workflow. And that's going to be these that I unchecked previously. And what you'll see is we have a gross rock volume calculation. So using our thickness grid from before, we can actually just get a gross rock volume. And so it's just going to use the thickness and the area and the polygon to give us just a volume number. Then what we're going to have is actually a loop where it will run through volumes of gas recovery factor. So we have a gross rock volume built in. Now we're going to run a loop that's going to actually look at different gas recovery factors. So from 10% to 20% or whatever we decide is our value. And so when I actually go to run this, I can get I have a dialog that comes up, and I get an initial recovery factor and I get an end recovery factor in an increment. So it'll run through and iterate through each of these values. So I'll just do 3 here. It's the 10%, 15%, 20% using this increment of 5. It's just telling me that it will overwrite some of these other XML values. And so what we'll see is we're actually getting some, oh, in this case, it's actually, I've run it on the total field area. So let me change my polygon situation here. So I'm actually going to change the polygon. So I've gotten it for the full field area. Now I want to get it for just my individual lease areas. So Petrosys polygon file. And it's going to be, need to check to make sure which ones these are. So I've got those and those. Okay. So I can run through actually and get all of those areas. So I can actually go back and just run it again. So now I have, for each of my lease areas, I now have a chart here. And the thickness, so it's for each slice. So in this case, it's giving us a volume for every 10 feet. We could refine that further if we wanted to, but this is actually pretty good for now because we can start to see that more or less it's the same except for some of our areas to the west. And what we can actually do then is export these either as a PDF or as some kind of image and plot them directly to our map so we can compare them visually. We can also look at these in as a web page or an HTML view or XML view in Excel. This is just an easy way of actually distributing these values. You can send these over via email quite easily. They're just small files. So if I plot those maps that I just, or those charts, excuse me, that I just produced, I can plot them directly on top of my lease area, so I know just visually. It doesn't give me an exact representation, but shows me kind of where my volumetrics are the best. And that really brings us to the end of the demo portion. But what I want to talk about a little bit is what the next steps might be. And one thing we could do is actually break down these volumetrics into a section by section. So it's more of a apples to apples comparison of the actual number versus just a relative look. We could also begin looking at things like the stimulated rock volume. So we actually have some, within our wells, we actually have some microseismic data, and there it's populating there, down here to the south. And we can start to look at, okay, well, am I actually accessing other intervals? And so that, I suspect that maybe what's going on down here to the south is that actually we're accessing intervals above or below that are contributing to the volumetrics. And I'll go back into my slides here just to kind of finish off. And so we went through that. That was a lot of back and forth between the surface modeling and the mapping windows, but we generated a handful of grids, structure, thickness, and porosity grids. Then we used those to actually get some volumetrics. And we got to take a look at some of the ways we can use our surface modeling workflows. So the further refinements I talked about previously, you can see here, it's the refining the volumetrics to a little more apples to apples on a smaller scale, looking at the simulated rock volume to see if we're accessing adjacent units, and evaluating other similar zones in the area. If you have any questions that come up later on, you can always email me directly. My email is there at the bottom of the screen. You can also email our support line to get some for your either specific technical questions or just if you're having issues with IT related things as well. You can contact us there, and yeah, anything that you want to take offline, I'm happy to help you with. All right, bye everybody.